Systematic treatment of equilibrium. Okay, last day before our big fall break. So, what's so important about what we're talking about today? If you take something like Pepsi, okay, we could find the pH of this solution. All you do is, it's aqueous, so just put a pH meter in there and you can get the pH. But, you know, if you're the Pepsi maker guy, that's too late. You want to know what the pH is going to be with all this stuff that you're making, right? So think about this calculation. What do you have in here? Well, what's going to contribute to the pH? All the acids. You got phosphoric acid. Okay, where's my pen here? You got some phosphoric acid. You've got some carbonic acid, right? Maybe some benzoic acid. Probably, maybe there's some citric acid. Nah, not citric acid. That wouldn't be in Pepsi. But the point is think of all the Ka reactions you could write. For this one, you could write 3 Ka reactions: a Ka1, a Ka2, a Ka3. For this one, there's 2 Ka reactions. There's a Ka1, there's a Ka2. Right, you could write all these reactions. Benzoic acid, right? It's Ka reaction. And then all those Ka reactions, all these equilibria are simultaneously valid. They're all intermingled, right? Like you're going to have hydrogen ion concentration written in every single one of those expressions. And it's the same number. And yeah, you can get it with the pH meter, but the point is, what is it going to be theoretically? So that's really what we're messing with today, is how to handle a real-life situation where there's multiple equilibria going on. And how do you handle it? For example, you have oh my goodness, 246.6 zeros in a 2 molar HCl. Andy, why would that be so hard? Why can't we just put that in the calculator and hit negative log and have pH?
Because you lose accuracy with every zero?
No. There's another contribution. And we've never cared about this before. We've always just did, oh, strong acid. Let's do negative log, we're done. But not when it's this dilute. What else? Because that would work if this was the sole contributor for the hydrogen ion concentration. But what else is contributing? And when you're at this concentration, it's pretty major. Water itself. All right? What did we call this? H2O falling apart into H plus and OH minus. We're not supposed to say falling apart. We're not even supposed to say decomposing. We're supposed to say, starts with an A, autoionization or autoprotolysis. So, yeah, so now, and this is on the order of 1 times 10 to the negative 7. So this is getting to be a major contributor now. So you can't just do, no, you're going to be wrong. What's the pH of 0.085 molar phosphoric acid? Okay, fine. We can write a Ka reaction, right? And the Ka reaction would be H3PO4 goes to H plus. And what ion? What would that be, Danielle? H plus plus H2 PO4 with a negative. And that's just Ka1. So then you go do ice, and you would like to say that the concentration of this H3PO4 is 0.085. Well, hang on. You've got this H2PO4. Write another Ka reaction, you've got HPO4. Right, another Ka reaction, you have PO4 minus 3. Oh, which dude's 0.085? They all are added up, right? Phosphate in all its forms would be this concentration. So the concentration of phosphoric acid plus dihydrogen phosphate plus hydrogen phosphate plus phosphate itself would be 0.085 molar. So I mean, this is getting ugly. Right? Concentration of carbonate in the solution of, you've got some solid, you've got some carbonic acid, and you've got some HCl in here. What is the concentration of carbonate? Again, it's tied up in multiple forms. So you have to take this simultaneous equilibrium into account. So, man, you should be really, really worried, but no fear. Right? Jackie, look at that. No worries. We just got to learn Smith's 5-step program. Okay? Okay. So we're not going to get to the 5-step program yet. In fact, we're only going to work on steps 1 through 4. Step 5 is the biggie, so we're only going to do steps 1 through 4 and have that be the homework for Monday. But let's do a little review first before we hit these steps. Write the general equilibrium constant expressions for Kw. Let's do that one first. Brandy, how do you write the Kw equilibrium constant expression? Oh, yeah, I guess it's something over something, but no. Yeah, you're thinking of Kw as Ka times Kb. No, we're not. That's not what we're talking about. The equilibrium constant expression. It's always products over reactants. So what was the Kw reaction? Oh, we wrote it.
Oh, H plus.
Yeah, the concentration of H plus times the concentration of OH minus divided by 1. Yeah, because we should have wrote a little L here. And that number is, what is that number? Danielle, do you remember what that number is? 1 times 10 to the negative 14. Very good. Okay, there's a. How do you write a, Desiree, how do we write in general our Ka reaction? What did we use in general? We said it was in general this. Something, Ka. Well, what was the reaction? Yeah, it's always product over reactants. What was the reaction? We wrote in general. A general way of writing an acid. You said it was HA. So all right, HA on the reactant or the product side? Anybody? On the reactant. It goes to H plus and A minus. Okay, so Desiree, that would mean Ka is going to be what over what? H plus in brackets, A minus over HA. Ka, a KSP. In general, Melissa, how would we write a KSP equilibrium expression? It would be, in general, it would be what over what? Yeah. Yeah, I think that's helpful, what she's thinking first. Think of this first. Solid goes to its into its aqueous ions. So you would say KSP in general is? Yeah, the concentration of the ions over 1. Right. So in general, okay. So we'll need that info. Writing charge balance equations for chemical systems. It says here, Ida, that charge balance equations can be written for a solution that contains charged particles. What charged particles? What are they talking about? We hardly ever call these things charged particles. We call them, it starts with an I. Ions, yeah. I don't know why I even wrote the word charged particle. Didn't think of that until now, right? But it contains charged particles or ions. Charge balance equations can be written for a solution that contains ions because the overall charge of the solution is always 0, right? Because you don't touch a solution and get zapped. Okay. So let's see what they're talking about, a charge balance equation. Somehow we identified, in this example, EX1, we identified all these different ions and all these different compounds. This is everything that's in solution. So it's not only the ions, it's everything. Okay, so all we're going to do is put all the cations on one side and all the anions concentrations on the other side. So cation concentrations, anion concentrations. But we're worried about charge. So if you write something that has no charge, would it even belong in here? No, has no place. There's no charge to it, so don't worry about it. What's the difference, though, between saying sodium ion, this is the cation side. Well, first let's just do that. Let's see if you can see what the problem is. Put all the cations over here. Oh, that's the only one, right? That's the only cation. All the anions over here. We have chloride, we have phosphate, and we have hydrogen phosphate, and we have dihydrogen phosphate. Okay, so this is supposed to be a charge balance equation. Do you see something that doesn't look right? Because we're worried about charge. You see something that doesn't look right? Right? Yeah, he has no charge on him, though, so he doesn't belong in there. What I'm looking at is this 3 or this 2. Right? If all we're interested in is charge, forget about the identity of the compound. All you're interested in is charge. If all you had was sodium and phosphate, that if you have one phosphate, you've got 3 negatives. Well, then you better have 3 times the amount of sodium. See what I'm saying? So really all you really got to do to write these charge balance equations is always take the charge and just bring it out front. Don't worry about the sign, though, because you already took care of the sign by bringing all the negatives on one side, cations on the other. So this would just be a 1 times sodium, a 1 times chloride, but a 3 times the phosphate, 2 times the hydrogen phosphate. So otherwise your charge isn't going to work out. So we need a 3 here and a 2 there. And then it's all good. You could make the whole thing equal 0, and then you just have, positive cation concentrations and negative anion concentrations. Everything would add to be 0. But it's kind of more, I think it's faster this way. Just to write all the cations on one side, all the anions on the other, and put the charge absolute value out front. I think it's faster and easier. Okay. But if you want to make it all equal 0, you can do that too. Just make the anion charges negative, the coefficients. Okay, so we're learning, what we're doing is we're starting to set up equations, is what we're starting to do. Here's a set of equations we're going to be writing. Here's another equation we're going to be writing. Okay? Here's the last one I'm going to talk about. Why am I talking about writing all these different equations? I don't remember, was this college algebra or what? Where if you have 5 unknowns, you better come up with how many equations? 5. Otherwise, it's impossible to solve. That's all we're doing. If we're going to have 5 chemical species in the solution that we got to solve for, yeah, we might only be interested in one of them. It doesn't matter which one. You got to have 5 equations if you have 5 unknowns. 3 equations, you have 3 unknowns, and on down the line. So I'm just going through how to write all these different possible equations that we're going to write so we can solve for stuff. Here's the last one, a mass balance equation for our chemical systems. Mass balance equations take into account the fact that when the concentration of a salt is known, the concentration of the cation in all its forms in the solution is equal to the concentration of the anion in all of its forms in the solution. So what am I talking about here? So we're used to doing ones like A, right? Where you can say the concentration, just looking at this, the concentration of the sodium ion has to be what, Jeff?
0.001.
And how do you know that?
It's a 1-to-1.
It's not only is it a 1-to-1 salt, but remember that rule that I was harping on. Anything with what metal is always 100% soluble? Alkali metals. So you don't have to worry about solubility. It's 1-to-1 like Jeff said. So the concentration of sodium is 0.001 molar. The concentration of chloride, everybody, is 0.001 molar. Now, all I'm doing is just going one step further. I'm saying the concentration of sodium in all its forms is 0.001 molar. Yeah, there's no other form other than sodium, right? The sodium is Na+. There's no such thing as Na2+ or nothing, right? It's just sodium. That's the only choice. Concentration of chloride, likewise, concentration of chloride in all its forms is 0.001 molar. No choice. Okay, now we're coming over here. If we do B, Kimberly, the concentration of sodium is going to be what? 0.002. Andy, you see that?
Yes, sir.
All right, you got the 2. Okay. Now, one thing that I'm really comfortable doing is when I see this stuff, I play with these polyatomic ions all the time. You probably haven't done it since general chemistry. So you got to go back and remember this stuff. Sulfate, the charge on sulfate, the answer's right here. It's the 2. What's the charge on the sodium? It's right there. It's right here. Right? It's that number that's right down there. It's a 1. And you also know it's in group 1. Okay. So the concentration of, oh, now this is getting weird, right? Because sulfate, what's the difference between sulfate in water and chloride in water? Does chloride react with water at all? Cl minus. If chloride reacts with water, if you say chloride reacts with water, that's a K what reaction? KB. That's a KB reaction, right? Because remember, we always took the anion plus water, didn't matter what it was, we called it A minus, and we got hydroxide and our conjugate acid. Can you form HCl, Danielle? Why not? HCl is a strong acid. You can't form strong acids, ever. This is not ever going to happen. So remember the story? That the conjugate bases of strong acids are so weak, they never do anything. So that's why we got by with saying the concentration of chloride is 0.001 molar. So when you do this one, you better do something first. If you're going to write a mass balance equation, you better identify everything that's in solution. Otherwise, how can you write a mass balance equation? All right? So, but anyway, maybe you can see it. The concentration of, maybe not the concentration, but you could say what molarity is equal to the concentration of sulfate in all its forms. What number? It's one of those 2, right? It's got to be 0.001 molar or it's got to be 0.002 molar. But which one is it? Brandy's right. Why is it 0.001? Because if you pretended sulfate didn't do anything in water, we know sulfate will because it's going to react with water and make HSO4. And you have a Ka for that. But the point is if it didn't, the concentration of sulfate would be 0.001 if it didn't do anything, if that was the only form. Because there's not no subscript 2 here. You're not multiplying it by 2 like you did for the sodium. So the concentration of sulfate in all its forms has to be 0.001 molar. Okay. So the concentration of sodium is 0.002 because when this thing breaks up, you have 2 sodiums. When you have 1 sulfate. The problem is I can't just write sulfate here. What other form does sulfate exist? HSO4 minus. Do I keep going and write H2SO4? It's the right thinking if you did. It's the right thinking, but you just have to remember the trick. You can never form what acids? Strong acids, and he's on our list. So that's why you erase him. But that's the thinking. You just keep doing it. And as long as it's not a strong acid, you keep adding your H's. As long as it's not a strong acid. Okay? See if you can figure out C. Write a charge balance equation for C. Now the question you're supposed to ask yourself is what? What molarity equals what compound in all its forms? What compound would I be referring to? The phosphate. It's the only thing that's there. You can't say hydrogen in all its forms. No, you never go that way. You never go no. It's phosphate. 0.00, what's the number here? Equals phosphate concentration in all its forms. What will be the number? 0.001. There's nothing fancy here, right? There's not a subscript with a 3 down here or anything. So the phosphate in all its forms is going to be 0.001. So identify all the different species that's going to tie up phosphate. Write their concentration, add them all up. All those, the concentration of phosphate in all its forms has to be 0.001. And if you're not sure, just imagine all the different Ka reactions you can write. All the answers are right there. So Ricky, what forms of phosphate are there?
H3PO4, like very little, and then H2PO4 minus, HPO4 2 minus, and PO4 3 minus.
Yeah. All right, now let me be devil's advocate. Oh, hold on. Last time we erased the fully protonated form. But it's not a strong acid, so you better not erase it. Exactly. Kimberly's right. All right? So a concentration of phosphate in all its forms has to be 0.001 molar. The amount of phosphate in a system is really, that's a very common issue and problem for a lot of systems. So this is a very common problem. Look how it's tied in with these multiple equilibria. Okay, so what we are going to do, yes, Andy.
What about the concentration of hydrogen?
Okay. All we're doing here is that we're writing one equation for the getting the mass balance equation. If you're interested in the hydrogen ion concentration, which we will be later on, that's probably, you're going to see it in a lot of different equations. You're going to see it in this, you're going to see it in this Ka reaction, the Ka1 reaction. You're going to see it in the Ka2 reaction. You're going to see it in the Ka3 reaction. You're going to see it there. You're going to see it in the Kw. Hydrogen ion is going to be all over the place.
So you're not going to worry about hydrogen ion when you're doing the mass balance equation?
For mass balance, no. Because we're always, good point. Because you're always going to be talking about some compound in all its forms, and it's never hydrogen, ever. It's always that darn anion, the guy that reacts with the hydrogen. Yeah, good question.
Water and what is it? Autoprotolysis is going on.
Yes, it messes it up. Exactly right. Exactly right. That Kw reaction messes up everything. So you're never going to have hydroxide or hydrogen ion in a mass balance equation. So general systematic treatment of equilibrium. Here's the problem. Using a systematic treatment of equilibrium approach, determine the concentration of each pertinent species in solution. So that means identify everything and determine its concentration. Here's the first one, 0.28 molar strontium nitrate. Okay, so it's going to start out easier and get more difficult. But the point is there's my 5 steps. Okay, and we're only doing steps 1 through 4. Big picture, day 23, Monday, that's when we finish it. Okay, so all we're doing is, if there's going to be 3 species, we have to identify 3 equations. If there's 5 species, we have to identify 5 equations, that sort of thing. Okay, so first, step 1 is looking at this and identifying all the unknowns, all the chemical species. So Kelly, looking at 2.8 molar strontium nitrate, what species would there be? What would be in solution if you had strontium nitrate? It'd be, okay, strontium with what charge? +2. And you also mentioned nitrate. Okay. Is there anything else? Can we write HNO3? No. All right, because that's the thinking you're supposed to do here is, hey, what can react with water? Think Ka, Kb reactions. And strontium isn't going to do anything with water. Nitrate won't either because it's a conjugate of a strong acid. So you're done. Okay. So we identified all of our species. That means we only need how many equations? 2. Nice. Okay. So write any Kw, Ka, or Ksp expressions. So looking at these ions that we identified, is there a Kw, a Ka, or a Ksp we can write? Is there a Ksp? Good question. I harped on the alkali metals, right? The alkalis, group 1. Always 100% soluble, the sodium, lithium, potassium. But there were some anions that I've been harping on too. You put these anions with anything and it's always 100% soluble. What were the anions? Oh, ammonium was another one. Goes with anything. That's a cation. It goes with anything. It's nitrates. And there's really only one more. Acetates. 100% soluble all the time. So you pretty much have to know these 2 general rules. Otherwise, you're going to start writing KSP reactions for something like sodium fluoride when it doesn't exist, right? So you can't look up a KSP for sodium fluoride. There's no such number because it doesn't exist. It's 100% soluble. So, man, you definitely, to do these problems, you definitely got to know this. Otherwise, you're going to be writing, right, some reactions like a KSP for this when you shouldn't be. There, it doesn't exist. Okay, so there's nothing to write. We're done with step 1. We're done with step 2. Write charge balance. Okay, Jackie. Let's write a charge balance. Remember the trick. Put all the what on one side and all the what on the other side. Cations and anions. Okay, strontium's over here. And anions over there. Are we done? So we do what?
Bring out the charges.
Bring out the charges. There it is. Okay. And oh, it says charge, and so there's our charge, our mass balance. Sabina, what can we do for our mass balance? This is the hard one, I think. You're getting there for each one, meaning strontium and nitrate. So in English, what helps me is in English, identify, okay, I've got strontium and I've got nitrate. So in English, I would say the concentration of strontium in all its forms is some big M. The concentration of nitrate in all its forms is some big M. That's mass balance. So what equation would you write? Anybody see it? Concentration of strontium in all its forms. There's only one form, right? So you just write strontium in all its forms is what big M? 2.8. And we can write one more. The concentration of nitrate in all its forms is 2 times 2.8. So we actually have more equations than we need. Right, 5.6. Okay. So this is making something, right now anyway, much more complicated than it needs to be. Because we could have just answered that in the first place. Strontium's 2.8, nitrate's twice that. But like I said, life is going to get much more complicated, so therefore the 5 steps. Okay, so try B. And then I'll see how far you can get. Try B. Oh, verify the number of unknowns is equal to the number of equations. So we've got 1, 2 unknowns, but we have 1, 2, 3 equations, so we're easy. Right? We have 2 unknowns. We have 1, 2, 3 equations, so we're done. We have more than enough equations to solve it. And B, try to set up B and realize it's a saturated aqueous solution. That's a hint. Notice I have a little S.
The S stands for that.
S stands for solid. And if you get B, go on to C. And I'll write down some solutions here, what I think are the solutions, and see if we all agree.
I have a question. Why is it 2 strontium, 2 plus?
Oh, because
Instead of,
do you see the little subscript 2 on the nitrate?
yeah, nitrate.
So that means that the charge on the strontium has to be plus 2.
Okay, but when you're writing the concentration in brackets, you put 2.
Because Jackie, remember Jackie's did that. She said that she put all the cations on one side, then all the anions on the other. And then it's charge balance. So she had to put the charge out front. Okay. So this is charge balance. So what they're saying is that the concentration of nitrate is twice that of strontium. That's how you could say it in English-wise. Whenever you see an equal sign, you say the word is. So the concentration of nitrate is twice that of strontium. And it is. Nitrate's 2 times 2.8, strontium's 2.8.
calculator for this one, or am I just like?
No, we don't need any calculators for any of this because we're not solving anything.
Oh, okay.
So can you write any other? Did you get that far on B? Can we write anything else? Or am I missing something? If we can't write anything else, can it be solved? We have two equations, two unknowns. It can be solved. All right? So KSP, you just got to, all those K's, you're assuming you're going to look them up, and you will. You'll have to look them all up. Try C.
Now for C, can you do a KB since the fluoride forms a weak acid?
Okay.
Since HF.
Let's start with step one. What species did you write up there?
Na plus and F minus.
Na plus, F minus. Okay. And what very often how I do this is when you've done this a lot, you can keep going on step one, but you have to be able to visualize step two. But I say you just follow logic, and logic dictates, right, sodium and F. Okay. Hopefully you can get by with this, right? So let's go on to step two. So you look at step two, and you're trying to write equilibria. Now you write a K, KB, because of the fluoride, right? So you write a KB reaction, or sorry, not a KB reaction, a KB expression, right?
So it doesn't have to be KA.
Yeah, yeah. So KB is going to be what over what?
HF. OH minus over
OH minus.
over F.
Okay. So once you wrote this is how I like, this is what I mean by logic. Once you write this, darn, now I have to add what to step one? Better add HF. Anything else? OH. Okay. Now that I added OH, go back and read step two again. Now you can write a KW, because now you have hydroxide. And look at all that. Now you got to write a KW.
You sound a lot more enthusiastic than I would be if this was not.
What do you mean if?
Way to go, Ricky.
Okay, now we know study.
Okay. But now what's missing in step one? H plus. No, this is real life. This is real life. Okay. Are there any other K expressions that you can write? You could write a KA. However, it's redundant. It's like, I don't know if you ever got to those solving a bunch of these equations and you get 1 equals 1. You're not introducing any new information. So either you write a KA or a KB. You don't write both because it doesn't help you. So just pick one or the other. So always. So we wrote KB, so we're going to quit there. We could have wrote a KA instead. That would have been fine, but we wrote the KB. So if you write a KA, you're still stuck writing KW, so it doesn't really matter. They're all there. Either or. Logic dictated writing a KB here because it fit. But you could have wrote a KA. Step 3 is charge balance. Write your charge balance.
So that means that all these that we put in number 1 would have to be in the charge balance.
Anything with a what? Only things with a charge. Only things with a charge show up. Last step. Do we need to do the last step? Man, because mass balance kind of sucks, right? It's kind of confusing. How many unknowns do we have? We have 5. How many equations do we have? 1, 2, 3. We have to, right? In fact, we better get how many equations out of this? I mean, out of step 4, we better get, well, 5 total. You got to get 2 more, right? Because we have 3. We need 2 more equations. Ooh, Kimberly saw one of them already. We're halfway there. She said Na plus is equal to what molarity? 2.1. Now again, it really helps me to say it say the way the mass balance, Smith wants you to say it. The concentration of sodium in all its forms is equal to what molarity? 2.1. The concentration of what? F minus in all its forms, or concentration of F in all of its forms, has to equal 2.1. So there's another one for you. Find fluoride in all its forms and put them over here. How many are there? 2. There's 2 of them. Fluoride has 2 forms. They both better be there. Those 2 forms are HF and F minus. Good. There it is. So we've got 5 equations, 5 unknowns. So now you've got the rest of your homework that you can mess with. So man, you're going to have fun this break. You're going to accomplish a lot.